All right. Okay, so welcome back. So today we'll keep talking about the sorting algorithms. And in our last lecture, we have actually implemented the pseudocode for Quicksort. Okay, and so we were at the step for analyzing the running times, right? So we will see that it's a little bit different in using the recurrence equations to analyze the quicksort. So it's a different from merge sort, because in merge sorts, we can see we can clearly know the size for the subproblems, but this is not the case in quicksort. Okay, let's look at the pseudocode, have some review a little bit. Okay, so the quicksort, actually, the first step, dividing step, is here by calling the partition procedure. Okay, and this partition procedure actually does some heavy lifting work, which is more work than the dividing step in merge sort, because in merge sort we simply compute the midpoint of a sequence, but this time the partition actually does more than that. It basically reorder all the elements by putting all the elements that are smaller than the pivots to the left, and all the elements that are greater to the right of the pivot. All right. So if we observe the next two recursive calls, we can also notice something different. So the first recursive call ranges from P to Q minus 1. And the second is from Q plus 1 to R. And their size is actually not determined, is not predetermined. It's not exactly half of the sequence. Actually, we have no information about how big those subproblems are. Right? It totally depends on the input. Depends on the input sequence. All right, and depends on the pivot elements that we choose. Okay, because by default, the pivot avenue is the last element in the input sequence. Right? Remember, in the partition procedure, we use the elements AR as our pivot elements. Okay, so if that elements have a different value, then the result of the partitioning of the partition procedure would also be different. Yeah, so the P is just the start of the array, because we use P and R instead of 1 and N, because this procedure will be recursively called. Right? So in this recursive call, the starting index might be different and the end index might be different. So we want to give it more a flexible arguments rather than fixed values. Okay. All right. So this is something we're gonna figure out today first. Okay. All right. So that means when we discuss the running time for quicksorts, the performance actually depends on the outcome, depends on the outputs from the partitioning procedure. Okay, and we use the word balanced versus unbalanced to describe the output of the partition. So we prefer a balanced output, and in the later slides we will see why. Because the balanced partition results would result in a better running time efficiency for the quicksorts. If it's unbalanced, then if it's extremely unbalanced, in the most extreme case, then quicksort can be as slow as inserted sort. Okay, so let's start from the worst case. Okay, let's just simply look at it. So this figure here indicates the result, the output from the partition procedure, right? Because the Q, the pivot, is already here in the middle. Okay, and everything to the left is the left half for the left half of the partition, right? From P to Q minus 1, and the right half is the input to the second recursive call. All right. So if we compute their lengths, there are two lenses, right? The left has the length Q minus P, and the right has R minus Q. So these lengths are unknown. It depends on where the Q is. Okay, but we know that they add up together to n minus 1 because we only take one element out. That we only take one pivot out. Okay, so according to our last slide, we say an unbalanced partition is a bad one, and in the worst case, the most unbalanced partitioning is, of course, that we will have n minus 1 elements in one half, while the other sub array has 0 elements. Right, that is the worst partition result we can have. So why not let's assume if this most extremely unbalanced partitioning occurs in every recursive calls, right? We must be very unfortunate to have that situation to happen, right? In every recursive call, whenever a partition procedure is called, it always results in this most extremely unbalanced partition. So that is, the partition procedure itself is a linear time function because it's basically a for loop, right? And so when the input is in 0, when the input has 0 elements, the sequence has 0 elements, then we say it's a constant time. That this is something we know for sure, right? So we can represent the solution to quicksort by this recurrence, because we assume that each partition will result in the most extreme split. The first half will have n minus 1, and the second half will have 0 elements. And this d of n comes with the cost for partitioning, right? So this is what we can get for the recurrence of quicksort, right? So now what we need to do is to solve this recurrence, and it seems not the form that we were familiar with using master theorem, right? We don't have the A times T of n over B, right? We don't have that proportional split. We only have n minus 1 as the first subproblem, right? So that seems to be a problem, okay? But this recurrence is still solvable, right? We can do some simple expansion, right? We can expand the right term here. We can expand the term for t n minus 1 into this form, into t minus 2 plus d times n minus 1, right? Plus d times n. And this t of n minus 2 can be further split into t of n minus 3 plus d n minus 2, right? we can do this all the way down to the smallest input size, which is T1. So when we have T1, we will have something appending to the equations. So this series is something solvable. It is very similar to the arithmetic series. Okay, so that means we can directly solve it. Okay, so having this guess, right? This is just a guess we can obtain, and of course we can also draw the recursion trees, right? When we don't have clues, we can work on the paper to split the root node into the several branches. And in this case, because we only have one branch, right? We only have one branch. So the recursion tree that we draw will be not very different from this formula that we write down in this one line of the equation. All right. So anyway, we can have a guess, right? We don't know yet. We don't know whether this is true, but we can assume that the solution is a quadratic function, because the summation of an arithmetic series is always a quadratic function. Okay. So having this as a guess, then what? We can try to prove it, right? We can try to prove this guess is correct using substitution method, right? So assuming the guess is correct in this smaller condition, when n-1 is the inputs, then this inequality should be satisfied, right? Assuming the guess is correct. Then we can substitute this into the original recurrence, right? Substitute into the right half, which results in this inequality. And we also wish the inequality to hold for the larger input size, which is this inequality, right? So in order to solve this inequality, right, this is what we get. We can basically have this inequality like C should be greater than or equal to this quantity, right? And this quantity has a limit because n can increase and then can be arbitrarily big. Okay, so when we can consider the upper bound of it, right? So the upper bound for this quantity quantity is achieved when n equals 1, right? Which means C should be greater than D. So that means our guess is correct if we make sure that the C is greater than D, okay? And then the n0 that we get is 1. Okay, so this is a typical solution, a typical process for using substitution method to solve the recurrence. All right, so that proves our guess, which means that, okay, let's go back to the previous slide. What we get is that if the take-home message, if the worst case partitioning happens at each recursive calls, then the solution, the running time for Quicksort is a quadratic function, which is as bad as insert and sort. Okay, but that is okay though, because we are very harsh to the inputs. We assume that every single recursive call would result in the worst results, okay, which is not likely to occur in real cases. Okay, but it's important to keep this in mind, right? Because when we want to be strict enough to, well, in our analysis, speaking of the lower bound of the algorithm, then we have to analyze this worst case. All right, so that's the worst case. So now what about the best case? Let's be a little optimistic now. And of course, the best case would occur when we have the most even splits whenever we have a recursive call. Whenever we call the partition, it always returns the most even. Okay, if we ignore the ceiling, the flooring symbols, we will have the equations, the recurrence equation like this. Okay, and this formula is something that we are very familiar with. And we have the constants, and then known function. Then we can immediately use master theorem to obtain a solution, which is big theta of n times logarithm of n. Okay, which is expected, right? Because it's quite similar to the case for merge sorts. When we have a even split on each sub-arrays. Okay, so having the worst case and the best case analyzed, what about the case in between? What about the average case? We are not likely to have to meet the best case for all the input sequences. And either way, we are either not possible, not very likely to see all the worst case. Okay, so actually, the average case is much closer to the best case than worst case in Quicksort. Okay, so what we're gonna do in these analysis and in the next slides is that we can consider the partitioning to always produce a proportional split. For example, on this slide, we only consider the partition that produce a 9-to-1 proportional split. Okay, that is to say 10% of the algorithm, or 10% of the input elements would be in one sub-array, while the 90% in the other one. And we assume that the partitioning is always proportional split. And of course, this is a simplified analysis. Okay, because we are only considering the average proportion. Okay, but let's see what would happen. Okay, so one thing we can definitely know is that because it's a proportional split, then our recurrence can be written as this form. One of the sub-array is 9/10 of the original length, while the other one is 1/10 of the original length. Okay, this is the same as the cost for partitioning, right? This one doesn't change. Okay, so given this new recurrence, we can quickly have the recursion tree plot, right? So 9/10 is here, so we assume that c equals 1, right? We ignore the c's in the nodes. So on the right we have, if we look at the first split, we have 9/10, 1/10, and when this one get further splitted, we have 9/10 times 9/10, right? Because it's always a 9-to-1 proportional split. We will have 81/100, and this one is 9/100, 9/100, 1/100. Okay, so we'll do this forever until we reach the smallest input case, right? But as we can see that this tree is not balanced. If we compare this rightmost branch, right? The decreasing speed for the rightmost branch is at the factor of 9/10, while the leftmost branch, okay, it decreases with a much faster speed. It decreases with the 1/10 speed, right? So here it should be 1/1000. Right? So if we observe the tree, then the leftmost branch will first hit the boundary, will first hit the smallest case, right? So this is not a balanced tree, but we can use some approximation to analyze the summation of all the elements of all the nodes in that tree, right? So what about we look at the cost for each row, right? The depth 1 adds up together to n, while the depth 2 also add up to n, right? 91 plus 81 plus 9 plus 9 plus 1. Okay, so that is something we can use to approximate the total summation. Okay, if we use logarithm of n to approximate the height of the algorithm or of the trees, then the solution would be big O of n times logarithm of n. Right. So that is to say, if we assume the tree is a very balanced tree, then the height of a balanced tree would be logarithm of n. Okay, and then we have that many depths, and each depth at each level, the summation is n. So in total, it would be n times logarithm of n. Okay, but we are not sure if this is correct. We need to prove it with substitution method. Okay, and luckily it turns out that if we use this as a guess for the solution and we submit it, we substitute it into this equation, we will finally prove it. It's correct. Okay, so it also tells us something very general about a tree structure. Okay, it tells us that even if the split at each node is not a perfect even splits, it's okay. Okay, so even if it's a proportional split, we can still get a very satisfactory total running time, n times logarithm of n. All right, so we're happy about it because this is a very conservative estimation. We are assuming that 9 to 1 proportional split on average. Okay, and this actually holds even if we consider much worse conditions. Okay, so it says with the 9 to 1 splits, we can have an n times logarithm of n as a total running time. And even if we use a much smaller proportion or much more extreme proportional splits, such as 99 to 1, we will actually have the same results. Okay, because we do the same analysis. We just change the number from 9 over 10 to 99 over 100, right? But that is still a constant proportionality. It's still a constant proportional split. Okay, basically any split of constant proportional will have a recursion tree that is at these steps. Okay, even though it is not a perfect balance tree. Okay, it can be right skew or left skew, but it's still, we can use this logarithm of n as the estimation for the total running time. And the cost for each level is also the linear function. So in total, big O of n times logarithm of n, no matter what split is, as long as the split has a constant proportionality. Okay, so this is something we can know when we analyze the Quicksort algorithm. Okay, all right. Being all these analysis here, that doesn't mean that we are happy with the unbalanced split. The unbalanced split comes with a cost, because when the tree is not balanced, some branches are longer. Okay, so our estimation may be correct in terms of the asymptotic property. Okay, but the constant factors will be different. We want the algorithm to be as close to the best case as possible. So we want to avoid the extreme unbalanced cases. So we want the split would result in we want the split would be as even as possible. Okay, So that's why we can do something to improve the quicksort algorithm. So it's called a randomized version for quicksort. And the idea is also very straightforward, right? In order to make the splits balanced, then we simply need to introduce some randomness. We want to randomly choose the pivots instead of always choosing the last element. Okay. So in this new version of partition procedure, which we call the randomized partition, we just randomly chose an index and exchange the position of the last element with it and call the original partition again, which is just one more modification, a simple with two steps modification, right? So this will be very beneficial to the algorithm, right? Because it introduces more randomness, and a random pivot means that it is the resulting splits on average would be more evenly distributed. Okay, and in a randomized quicksort version, we just call this randomized partition instead of the original partition. Okay, so this is some technique that we can quickly adopt in order to make the quicksort run faster. So I see a comment. If you're trying to sort something with quicksort, wouldn't a randomized partition have the same partition probability of n-1 to 0 as non-randomized? So the randomization is based on the idea that we don't know anything about the input. So it is possible that the input already has some structural information. For example, if the input is already partially sorted, for example, then the last elements can result in a very extreme partitioning result, right? So if that is possible, then we would have a very extreme partition in the as shown in the worst case. Yeah. So it is possible that the randomized partition can choose the largest or smallest, but it is not likely that each time it will always choose the largest or elements. Okay, if the inputs is not randomized, okay, we are probably it is likely that we are facing some inputs that is already partially sorted, that is already had some structural information in it. So we want to avoid that prior information, and we want to create as much randomness as possible. Okay, because speaking from a statistical perspective, the more randomness we provide to the more random operation we conduct to the input sequence, then it is more likely we are going to choose some very random pivot very random pivots elements. Okay, which is closer to the mean value or the median values. Yeah. All right. So okay, let's finish this slide for quicksort, and then we can enter the next sorting algorithm. Okay. So Speaking of the advantages, I think it's quite obvious. The Quicksort is a fast algorithm. Okay, the average case is very efficient. Okay, and it also doesn't cause any consume any additional storage space, which is an advantage over merge sort. Okay, and also there are disadvantages, like there's some, we want to create some randomness in the partition step. So I see a point. Choosing a random number, a constant. So actually, it's I need to look into that. I need to look into the algorithms for generating random numbers. So the current method that we use is usually to generate a pseudo random series by operations that compute the prime factors of a large number, something like that. Like we need to feed into something called a seed, and then it will generate a series of pseudo random numbers. But I think that function is a very efficient function. Yeah, it shouldn't be a let's see. I think it should be a linear running time algorithm. Yeah, or a constant running time. I think it's a constant time. Yeah, but I need to look into that. Yeah. And another disadvantage is that it's a recursive algorithm. So as any recursive algorithms does, it has to use the stack. Okay. Yeah. All right. That's the pros and cons for Quicksort. So next, we were done with our first sorting algorithms introduced. So next, we're gonna introduce the heap sorts. Okay. So let me stop the video. Stop the recording.